Hello there, welcome to my channel, Chemistry Lessons. Thanks for subscribing, those that have. I think I've got 52 at the moment, which is great. If you haven't, why the heck not? Make sure you do. If you have subscribed, then let's get your friends. Let's get this juggernaut moving. Okay, I appreciate that we're studying chemistry and we probably don't have that many friends, but it's great. Let's just get as many people going as we can. Thank you, I appreciate it. This lesson follows the AQA A-level specification and is an inorganic lesson. It covers the first section of Group 7. So there's going to be 2 lessons on Group 7, and this is the first of 2. And it's the final section on AS inorganic. So AS inorganic has 3 topics to it. It has 3.2.1 periodicity, 3.2.2 Group 2, and then this section, which is 3.2.3, and it's Group 7. Let's start by looking at the specification, and you can see it's quite lengthy. There's quite a lot to this topic, which is why it's going to span 2 lessons. So lesson 1 is going to focus on the left-hand side here, and we're going to start off with electronegativity and boiling point, and the video will work through all the way down to the trends and solubilities of halides, and the second video will then look at the uses of chlorine and chlorate. A good place to start would be a quick recap from Gcse in terms of what you should kind of bring with you from Gcse. So we look at the reactivity. If you recall Gcse, you did the reactivity of Group 1 and you also did the reactivity of Group 7. So in an earlier topic when we looked at Group 2, as you go down a group of metals, the metals become more reactive because the outer electrons are further away, and when a metal reacts, it's losing the outer electrons, therefore down a group metals become more reactive. However, when we look at Group 7, we look at the halogens. When they react by gaining electrons to get a full outer shell. So this time the reactivity decreased down Group 7. So chlorine was more reactive than bromine, and bromine was more reactive than iodine. And that's because they are smaller, they have less electron shielding, smaller radius, they're able to gain those electrons more easily. So reactivity decreased down the group. And in terms of appearance, chlorine was a green gas, bromine was an orange-brown liquid, and iodine was a grey-purple solid. So those are the things you should have from Gcse. Okay, pale green gas for chlorine, orange-brown liquid for bromine, and grey/purple solid for iodine. Gas, liquid, solid. Let's move on to electronegativity then. This may be a term you're familiar with from the covalent bonding topic. It may not, but let's remind ourselves of a covalent bond because this term is associated with covalent bonds. So we've got 2 atoms there, A and B, and the covalent bond is the electrostatic attraction between a shared pair of electrons and 2 nuclei. That was our covalent bond. Now, electronegativity is a measure of the ability that these atoms have to attract this bonding pair, because you've got 3 scenarios here. This bonding pair of electrons could be perfectly evenly shared, which means that A and B pull those electrons evenly. Or you could have a scenario where A is more electronegative, which means the electrons are pulled closer towards A. That would mean that A is more electronegative because it's pulling the electrons towards itself, which would give you a slightly negative charge on the A and a slightly positive charge on the B. And of course, the third scenario could be that B was more electronegative and the electrons are in fact attracted more towards the B, which becomes delta or slightly negatively charged, and leaving A slightly positively charged. So in this scenario, in the second scenario, A would be more electronegative than B. In the third scenario, B is more electronegative than A. And in the first scenario, they both have the same electronegativity. Okay, so if we try and verbalize this, it's quite a lengthy one, but electronegativity, it's the measure of the ability of an atom to attract the bonding pair of electrons in a covalent bond. So we're measuring the ability that an atom has to attract the electrons in a covalent bond. So this one, A, is more electronegative because it's got more attraction to the electrons. In the third scenario, B was more electronegative because it was attracting electrons more than A. And in the first scenario, we had equal electronegativities, which meant we had an equal share. Notice the slight charges that you see as a result of a difference in electronegativity. So what factors affect it then? So let's think about this. If we've got A and B sharing electrons, what do we know about the ability to pull electrons? It's the same factors we've looked at over and over again. It's the nuclear charge, the radius, and the shielding. So it's those same three factors. If you've got a small radius with less shielding, you're going to be attractive to those electrons. If you've got a big radius and lots of shielding, you're going to be less attractive, so less electronegative. So we're going to look at the periodic table now and have a look at how we can use the position to make our predictions of electronegativity. Now, the trend is the least electronegative at the bottom left, the most electronegative all the way up here at fluorine. Fluorine is the most electronegative, francium being the least electronegative. We ignore group 8. Now that might sound confusing, but the reason we ignore group 8 is because group 8 will not form bonds. They won't form covalent bonds, therefore we can't measure their electronegativity. So as you go from left to right, electronegativity increases. As you go from bottom to top, electronegativity increases. So you're going to need your periodic table because you're going to have a go now at making some predictions. You're going to use the periodic table to predict which of those pairs are the most electronegative. So pause the video, and when you're ready, press play. With your explanations, try and use the terms radius or nuclear charge or shielding, so try and explain them. Okay then, so F or N? Well, they're both in the same period, but N is further to the right. Sorry, F is further to the right. So F is the most electronegative out of those two because they have same shielding. F is smaller and has a bigger nuclear charge. So F has a bigger nuclear charge, has a smaller radius, and they have similar shielding. So it's the same explanations, the same kind of theory we're using throughout this whole ionization energy, electron affinity, electronegativity. And electronegativity and electron affinity are very, very, very closely linked. Right, O or S. And again, O is above S. O has less shielding, has a smaller radius, therefore O is more attractive to the electrons in a covalent bond. O is more electronegative. And for the exact same reasoning, Cl and Br are in the same group. Cl has a smaller radius, less shielding, it will be more electronegative because it's more attractive to the electrons in the covalent bond. Cl and F, this time F is above Cl. It's got a smaller radius, it's got less shielding, it's going to be more attractive to that shared pair of electrons, it's more electronegative. P or Cl in the same period this time, so they have the same shielding or similar shielding. Cl will have a smaller radius and a bigger nuclear charge. So Cl has a smaller radius and a bigger nuclear charge, therefore is more attractive to the electrons in a covalent bond. It's more electronegative. Moving on to boiling point then. So if we're asked about boiling points and melting points, That means that we've been asked to discuss the structure and the bonding. So this is a structure and bonding question. Now we're just focusing on group 7, so we'll look at fluorine, chlorine, bromine and iodine. Now in terms of their structure and bonding, these elements all exist as diatomic. So chlorine, fluorine, bromine, iodine, they're all diatomic. They exist as simple molecules, and the forces of attraction between their molecules is van der Waals, because they are non-polar molecules. So recall your knowledge on structure and bonding here. So they all exist as simple molecules. They all are held together by weak van der Waals. So we know they all have low boiling points, but we're asked for the trend. Now, remember or recall your knowledge on van der Waals. So this requires you understanding the van der Waals. Now, van der Waals was due to random movement of electrons, which caused temporary dipoles, which then caused induced dipoles, and we had an attraction between the induced and the temporary dipoles, and it was only weak. Now, the more electrons you've got, the stronger your van der Waals, okay? Now, as we go down this group, the molecules are bigger, despite the fact they're all diatomic. Something like iodine has significantly more electrons than fluorine. Therefore, the van der Waals forces between two iodine molecules is much greater than the van der Waals force between two fluorine molecules. So as we go down the group, the boiling point increases, and that's because more energy is needed to break the bonds between the molecules, because the van der Waals forces between the molecules become stronger down the group due to the fact that we have more electrons. So, and you'll see that the fluorine has the lowest boiling point, then chlorine. Fluorine and chlorine are actually gases at room temperature. You may recall from Gcse that chlorine is a pale green gas, bromine was an orange-brown liquid, and iodine was a grey purple solid. Why am I putting gas? It's a grey purple solid. So there is an increasing boiling point down the group, no exceptions. And that's due to stronger van der Waals, due to having more electrons and stronger temporary dipoles and stronger induced dipoles, more energy being needed to break those bonds. Right, we've looked at explaining the trend in electronegativity, and we've explained the trend in boiling point using their structure and bonding. So we've completed the first part, okay? First part completed, mate. Right, so we'll now look at this section here. So the trend in oxidizing ability of the halogens down the group, including displacement reactions of halide ions in aqueous solution. Sounds quite scary because there's a couple of quite technical words in there. So let's have a look. First thing we need to do then is look at this term oxidizing ability, and I've underlined the halogens here. It's worth remembering that we're looking at the elements. So when we talk about halogens, we talk about the elements, so F2, Cl2, Br2, they exist as diatomic. And when we talk about halides, we're talking about their ions, fluoride and chloride, bromide, etc. So fluorine is F2, fluoride is F-. Make sure you have that very clear. Now we're looking at the term oxidizing ability. Now, you hopefully are familiar with the terms oxidation and reduction. Okay, it is an earlier AS topic that you may or may not have covered yet, but again, these are terms that you use at GCSE, the oxidizing or oxidation and reduction or redox. Oxidation is the loss of electrons and reduction is the gain of electrons. Now, the oxidizing ability, this is measuring how good the halogens are at oxidizing other things, okay? So it can be confusing, and the analogy I use here is if you're an estate agent, it's your ability to sell houses. You're not selling your own house, you're selling other people's houses. So your oxidizing ability is how good are you at oxidizing other things. So if you're going to oxidize other things, you are causing other things to lose electrons, okay? Which means you are gaining electrons. Okay, so if you are oxidizing something else, that means in return you are taking electrons from something, so you are being reduced. So we could change this phrase into actually measure how easily are halogens reduced. So halogens being reduced. Okay, it's the same thing. If you're an oxidizing agent or oxidizing ability, it's measured by how good you are at taking those electrons. Now, when you think of it in terms of our factors that we consider in terms of gaining and losing electrons. So when we talk about gaining and losing electrons, we always talk about the radius, we always talk about the electron shielding, and we always talk about the nuclear charge. Okay, and we see this trend over and over and over. As we go down the group, the radius is increasing, the electron shielding is increasing. So the radius is increasing because we have more electron shells, and the electron shielding is also increasing because we have more electron shells or inner shells. So despite the fact that we have an increase in nuclear charge, these two factors outweigh it. So as we go down the group, their oxidizing ability decreases. So fluorine is the strongest oxidizing agent, or has the strongest oxidizing ability of all of the halogens. Second in that list would be chlorine, then bromine. So as we go down the group, their oxidizing ability decreases simply because they become less attractive to electrons. Okay. Let's look then at using this oxidizing ability and having a look at displacement reactions in aqueous solutions, and let's be prepared to make observations. So in aqueous solution, you will notice that the colour gets darker as we go down. In aqueous solution, we've got a very pale yellow, pale green for fluorine. You'll accept pale yellow, pale green. Chlorine is pale green as well, but it's a slightly darker shade than fluorine. And bromine is an orange brown, and iodine solution is actually a dark brown. We can see that we've got it as a purple grey solid, but in aqueous solution, iodine is a dark brown. So we've got pale yellow, pale green, orange brown, dark brown as we go down. Those are the observations, those are the colours that we would see in aqueous. And once we know those colours, we can apply our observations when we look at displacement reactions. Right, let's see what's happening then when the halogen is acting as an oxidizing agent. We've said that it will gain electrons. So it will become negative. So fluorine will become fluoride. It will do that by gaining electrons. Okay, so to balance it out, a fluorine will gain 2 electrons to become 2 fluorides. Okay, and if the fluorine was going to be oxidizing a group 7 element, so it says aqueous solution. So I'll give an example here. We've got fluorine reacting with sodium chloride solution. So we're in aqueous solutions here. Okay, so the colour of our reactants here will be a very pale yellow because of the fluorine. This is going to be colourless. Salt solution will be colourless. So the starting colour here will be a very pale yellow, and the displacement will occur because the fluorine can displace the chloride. Notice the terminology. Fluorine is displacing chloride. It will become sodium fluoride, which is colourless, and chlorine. And again, this is aqueous. So the colour change here will become darker. We will go from a pale yellow to a pale green. Okay? And we'll see those observations and those changes taking place. So let's have a look. If I was to call bromine, this would start as an orange brown. If it was to react with sodium iodide, again, colourless. So the overall colour of the reactants here will be orange brown. We will get that displacement, which will become sodium bromide and iodine, again, aqueous solution. So this solution will go from an orange brown to a darker brown. You will observe the colour get darker. So if the displacement takes place, and it will take place if the halogen is more reactive than the halide. Okay, so if you get the displacement taking place, be prepared to give an observation. Okay, and we know the colours of the aqueous solutions. So you can't just say it gets darker. Say that orange brown to a dark brown, or pale green to an orange brown. Okay, and those are the displacement reactions, when the more reactive halogen displaces a less reactive halide. And I'm going to come back now to my ionic equation, or sorry, not ionic, my half equation to start. I was showing the reduction of fluorine to fluoride. But what also is going to happen here then is the chloride will become chlorine, and it will do so by losing 2 electrons. So notice how the opposite is happening. The fluorine is acting as an oxidizing agent and is being reduced to fluoride. And in being oxidized, the chlorine is losing electrons, and it's going from chloride to chlorine. Be careful with the terminology, ides and gens, so halogens, halides, okay? Time for you to have a go then. So what you're going to do is, for each of these following questions, particularly for questions 1 to 4, you're going to construct a balanced symbol equation, and you're going to give any observations that you will see. You may wish to challenge yourself by having an attempt at giving half equations to show the redox reactions taking place as well, so to show the oxidation and the reduction. Question 5, again, it's an ionic equation you're being asked for in number 5, so a little bit of a test of your ionic equation knowledge. So pause the video, and when you're ready to go through, unpause. Right, well, the first thing we should do is double check that there's actually a reaction going to take place, okay? Because you're only going to get the displacement if the halogen is more reactive than the halide. And remember, we can determine the reactivity based upon the position in the periodic table, and chlorine is more reactive than bromine, so you will get the displacement of chlorine with bromide. So here we're going to get NaCl, aqueous, plus Br2, aqueous. And our observation here, don't forget to balance it, our observation here is going to be from a pale green solution to a orange brown solution. Remember, the colour is this. This won't have a colour, so the colour is pale green solution becomes an orange brown solution. Next one. Is bromine more reactive than iodide? Yes, it is. So we will get the displacement taking place here. It will become KBr plus I2. Aqueous and aqueous. We must balance it though. And our observation this time, colourless and colourless, so we don't mention those. It will go from a orange-brown solution to a dark brown solution. You'll actually get away with a grey solid if you were to say that observation, but we want a dark brown solution here. And third one, bromine, chlorine. Well, I've put this one to try and catch you out here because there's in fact no reaction. So don't just go into autopilot, okay? There's no reaction there. And the last one, fluorine. Yes, we will have a reaction taking place. It will become NaF, aqueous, plus Br2, aqueous. Don't forget to balance. So here we'll go from a very pale yellow solution to a dark brown, well, sorry, no, an orange brown solution. Okay, so the solution will go from a pale yellow to an orange brown solution because these two are colourless. And in terms of your ionic equations, for the last one, give an ionic equation for the reaction between chlorine solution, so chlorine with potassium bromide, and it's aqueous. It's aqueous. Is there a reaction? Yes, there is. So let's do the full equation first. We'll have KCl. Let's balance it 2 and 2 plus Br2, aqueous. Now, if you recall your rules for aqueous solutions, if it's an ionic substance such as KCl and KBr, we would draw the ions out. And if you were to go through your procedure, you will find that the potassium ions are spectator ions in both cases, and in which case the ionic equation comes out at Cl2 aqueous plus 2Br minus aqueous becomes Br2 aqueous plus 2Cl minus aqueous. And I did mention challenging yourself. I'll do one of them because they follow a pattern. The redox reactions here, we would have Br minus at the top, we'd have Br minus becoming Br2. And in doing so, it's losing electrons. It's losing 2 electrons because there's 1 for each bromide. So it's 2 Br minus goes to Br2 plus 2E minus. That's showing the oxidation of the bromide. Now the reduction of the chlorine is the opposite. It's gaining 2 electrons. So 1 electron for each of the chlorines to become 2 chlorides. So that's showing reduction and that's showing oxidation. Okay? Right. So we've seen the trends and explained the trends in electronegativity and boiling points. We've looked at the trend in the oxidizing ability and we've explained that or shown that using displacement reactions of the halide ions in aqueous solution. Now, this is the most dreaded and hated part of halogens. People really dislike this topic. So let's try and kind of strip it back and try and look for a pattern. Okay. Okay then, so let's have a look at this, the reducing ability of the halides. So we are measuring the ability, the halide, notice it's a halide, so we're focusing on the F minus, Cl minus, etc. They are halides, so they are F, like fluoride, chloride. It's the reducing ability, so how good are they at giving electrons to something else? Because if you are going to reduce something, you are causing it to gain electrons. So in other words, it's the ability that the halide has to give that electron to something, okay? So reducing agents will donate electrons. So therefore, halogens are not reducing agents, halides are, okay? Just as we saw that halides weren't oxidizing agents, halogens were. So halides can be reducing agents because they are, well, they have that electron that they could give. Now, as we go down the group, their reducing ability increases. And again, use those 3 factors. So as we go down the group, the radius increases, the ionic radius increases, they're ions now, their ionic radius increases, their electron shielding increases. That means that iodide is more likely to get rid or donate its electron than fluoride, okay? Now, the most common source of halide ions are sodium halides and potassium halides. So sodium chloride, sodium bromide, sodium iodide, or potassium bromide, potassium iodide. Now, we have to use concentrated sulfuric acid, or we have to be able to use concentrated sulfuric acid to show the reducing ability. So the first thing that I suggest we do is we look at sulfuric acid and we look at some other sulfur containing compounds and their oxidation states. Now, if you're in a position to assign the oxidation states, because if you've done 3.1.7, the physical redox topic, then you're in a position to assign oxidation numbers. If you haven't done that topic yet, then you're not, okay? So we can assign oxidation states. So I suggest you pause the video and have a go at that if you can. If not, unpause it and we'll see those oxidation states. So the oxidation state of sulfur, it's just the sulfur that we're looking at. In H2SO4, it has an oxidation state of +6. In NaHSO4, oxidation state of +6. SO2, +4, 0, and -2. So what's happening there is the sulfur is being reduced. Okay, the sulfur is being reduced. And the most common source we've said is the sodium halides or sodium or potassium halides. And we can see that the iodide is going to be the best reducing agent, fluoride being the weakest. So this is what we see. So we're going to use concentrated sulfuric acid, hence H2SO4, that's concentrated sulfuric acid. So we're going to use sulfuric acid that has sulfur of the oxidation state of +6, and we're going to measure how much can it reduce it, okay? So the best reducing agent will reduce it all the way to -2, and the weakest reducing agents maybe don't reduce it at all. So let's start off. So fluoride, chloride, bromide, iodide, all 4 halides will react with sulfuric acid to make NaHSO4. That is not a redox reaction, so there's no reducing going on there whatsoever. So that does not show the reducing power, but the chemical reaction will take place and you will see NaHSO4. We'll look at some equations in a minute. Now, that's where it stops for fluoride and fluoride and chloride. So you'll notice the fluoride and chloride will not react further because they are not good enough at reducing sulfuric acid. So you don't get any reduction taking place with fluoride or chloride. However, with bromide and iodide, they can reduce sulfuric acid to make SO2. Sulfur's gone from +6 to +4 in that situation. And that's where it stops for bromide. Bromide can't reduce the sulfuric acid anymore, but it can reduce it to make SO2. Iodide kind of shows off because the daddy of the halides when it comes to reducing. Not only can it reduce it further to sulfur, the iodide can actually reduce it all the way to H2S, which is -2. So iodide can reduce sulfuric acid all the way down to H2S. Iodide and chloride, fluoride and chloride can't reduce it at all. So let's have a look at what those equations will look like. And again, we need some observations here. So all of them will do that reaction. Every single halide will undergo that reaction, okay, to make the NaHSO4. And the observation here is misty white fumes. We'll see misty white fumes because of the HX, whether it's HF, HCl, HBr, HI, we're going to get some misty white fumes, and that's in all cases. Not a redox reaction though, okay, we've seen that. It's not a redox, it's just an acid base. And that's the only reaction that takes place for sodium fluoride and sodium chloride, so we don't get any redox because their power or their reducing power is insufficient enough to do any reducing. Just to remind you there that the fluoride and the chloride will not reduce it. It will only react to make the NaHSO4, as do all four of them. So you'll see misty white fumes. That is one observation for all four of them. When it comes to sodium bromide and sodium iodide though, they will undergo a further reaction because they are able to reduce the sulfuric acid rather than just react with it. So we actually get a redox reaction taking place here because of the reducing power of iodide and bromide being better than the chloride and fluoride. So not only do we see those misty white fumes of the HX, you're also going to see the X2, which in the case of bromine means some brown vapor. Note how it's a gas, so when you add NaBr to concentrate sulfuric acid, you're going to see misty white fumes and a brown vapor. And we're explaining that because the misty white fumes are the HBr and the brown vapor is the Br2. When it comes to iodide, you're going to see the HI white vapor or misty white fumes, but you're also going to see a purple/grey vapor on that one. You won't see anything of the SO2 because that's a colourless gas. So we see those further reactions. Now, the iodide will actually go on further, okay? So the iodide is the daddy of reducing when it comes to the halides, and we have the further reactions. We're going to summarise all these observations and reactions on a later slide. And it's worth making yourself some flashcards. So there we go, just a reminder of what happens. All four will react to make the NaHSO4 and your misty white fumes. Bromide and iodide are sufficiently strong enough reducing agents that they'll reduce it to SO2, in turn making bromine and iodine vapours. And you know the colours there, the brown vapour for bromine and purple grey vapours for the iodine. Iodide, however, will go further. So let's have a look at what the iodide can do. Okay, so with iodide, we get the misty white fumes for HX or HI. We'll get the purple vapors for I2, but we also get a further reaction to sulfur solid. Now, sulfur solid is a yellow solid. So we've got observations here of misty white fumes from HX. You've got your purple or violet vapor of I2, and you've got a yellow solid for sulfur. And it does even go further. We said it goes an extra step. So again, we get the iodine, which is just your purple or violet vapor. And H2S is a rather nasty rotten egg smelling gas. So you've got plenty of observations there. You've got rotten egg smell, you've got yellow solid from sulfur, you've got vapor, purple vapor from iodine, and you've got the misty white fumes of HI. So there's a lot going on there. Again, just reminding us that iodide's the strongest. It will reduce the sulfuric acid all the way to sulfur and H2S. The bromide will reduce it to SO2, which you can't see, but in turn you do see the brown vapor of bromine gas. And when it comes to fluoride and chloride, we don't get any other observation other than the misty white fumes of the acid-base reaction. There's an awful lot happening here. I can understand why people don't like this topic. So flashcards are your friend here, but being able to understand the science behind why they are better reducing agents and understanding where the observations come from does make it an awful lot easier. So in summary, when you add sulfuric acid to solid sodium fluoride, you will get misty white fumes, and that's it. The misty white fumes are the hydrogen fluoride. When it comes to chloride, you get the same observation. You get misty white fumes, which is hydrogen chloride. When you add sulfuric acid to solid bromide compound, you will get misty white fumes of hydrogen bromide, along with some brown gas of the bromine. And finally, with iodide, you're going to get your misty white fumes, you're going to get black-grey solid of I2 or purple fumes, and you're going to get your yellow solid from sulfur and a rotten egg smell from H2S. So those are your observations, okay? It's worth making notes of those, particularly on revision cards. And normally, this isn't kind of the test that we'd use for halides. We're going to see that in a later slide. So testing for halide, you wouldn't normally use concentrate sulfuric acid because it is highly corrosive, highly toxic. It's not really nice stuff to be using. Okay, so next time round, you see it in a couple of slides actually, we're going to look at how we can actually a better test for halides, which you did see at GCSE. So we're making our way down here quite quickly then. We've looked at electronegativity, we've explained them, we've explained melting points, we've looked at oxidizing ability of halogens and explained that with observations. We've also looked at the trend in reducing ability of halides and observations. There's a lot to that. People hate it. Me too. But you know, it gets us our grades. That's what I look like, in case you're wondering. Finally then, having a look down at the use of acidified silver nitrate to identify and distinguish between halide ions, and then the use of ammonia. This bit is actually comes from GCSE. You've seen this before. The ammonia bit is new. Right, last section then. So we're looking at using acidified silver nitrate and ammonia to identify halide. Now, halide ions are negative aqueous ions. So we're looking at the halide ions. They are all colourless. So chloride, bromide, iodide ions, aqueous ions are colourless. And silver nitrate is AgNO3. And again, that's a solution, aqueous, and that is colourless. So we're using observations here. We're looking at the formation of precipitates to identify halides. We'll come back to that. I want to look now at why it's acidified. So it must be acidified silver nitrate. If you just call this silver nitrate, you're not going to pick up your mark. You need to call it acidified silver nitrate. And that's because the acid will remove any impurities that could affect your observations, such as carbonate. So the acid will remove any impurities of carbonate, which could affect your results. Okay, so that's why it's acidified. Right, now what happens here is, it's easier to show as an ionic equation. It's the silver ions that are forming a precipitate with the halide ions. You're forming a silver halide precipitate. Okay, you may remember this from Gcse. Now, silver chloride precipitate is white, so you're adding silver nitrate to a solution, and if you form a white precipitate, that means chloride ions were present. I'm not going to do the state symbols in all of them. If you added bromide, you get a cream precipitate of silver bromide. And if you add iodide, you get a yellow precipitate of silver iodide. Notice how the colour gets darker down the group. White, cream, yellow. Chloride, bromide, iodide. And that was straight from GCSE. You know, this, had you done higher level GCSE, you have seen these ionic equations before. The only new bit for us is this use of ammonia. Now, the reason being is, in reality, trying to distinguish between a white and a cream precipitate is quite difficult. Okay, you may hold up a cream solution to someone and they might say, sorry, a cream precipitate, and one student might call it yellow, the next student might call it cream, someone else might call it white. So that they are quite difficult to distinguish between. Okay, and you can use ammonia to do that. Okay, we use dilute ammonia. So first of all, you would add dilute ammonia. And if you add dilute ammonia, this will dissolve in dilute ammonia. So if you add dilute ammonia and the precipitate disappears, that means it was silver chloride. Now, if you were to add dilute ammonia and it doesn't dissolve, that means it was either cream or yellow as bromide or iodide. So if it does dissolve, it was chloride. If it dissolves in dilute ammonia, it was chloride. If it doesn't dissolve in dilute ammonia, that means it's bromide or silver iodide. So the next thing you do is you then add concentrated ammonia. And if it dissolves, that means it was bromide. If it doesn't dissolve, that means it was iodide. So it's kind of like your secondary check. So you add the silver nitrate to get a precipitate. If you get your precipitate white, cream, yellow, you can then confirm that precipitate by using ammonia, because dilute ammonia and it disappears, that means it's this one. If it doesn't disappear, it's one of these two. And if you then can use concentrated, you add concentrated and it disappears, it's bromide. If it doesn't disappear, it's iodide. What I suggest you do then is you make some revision cards based on these notes here. We call these a box of 8. It's to make some revision notes. You won't be able to do all boxes until you've actually seen the second lesson as well. So maybe pause this. You should be able to do the boxes you should be able to do after this lesson. This is just a bit of a revision really of ionization energies. You should definitely be able to do this one. You should definitely be able to do this one. You should definitely be able to do this one, and this one. Okay, these two we won't be able to do yet. Hopefully you've enjoyed that. Again, you know what you're doing. There you go. And I'll see you in the next video. Or I won't see you. I won't even hear you. But you'll hear me. You won't even see me. Good luck.